sir?
I just press record button. I don't know what this does.
Oh, okay. Anybody
Yeah,
else
it
know?
says your video call is being recorded.
Okay. So, hi everyone. Let's begin. So, first I want to say that this is not going to be technical. I mean, it is going to be technical, but not in the formal way. So, it will be, using illustrations and visualizations and stuff like that rather than equations or, scary symbols. So I just want to say that this is going to be very interactive. So it will be better if you also ask questions or participate in the discussion. So let's just begin. For starters, I will be showing you 5 solids. So some of them you'll be familiar with and some of them you won't be. Yeah, so let's start with a simple. So what is this? Can you see? What is
Position it
this?
little center of the screen.
What, sir?
Ah,
I can't hear
yeah,
you.
that is better.
Huh? Yeah. What is
Yeah, yeah.
this?
This is better position.
Yeah. What is this? I'm just rotating. I expect you to say something. I mean,
Tetrahedron, huh?
yeah, tetrahedron. So it's made up of how many equilateral triangles?
Four.
Sure. So 4 equilateral triangles make a
Four.
tetrahedron. Yeah. Next, again, very, very familiar. What is this?
So cuboid.
Cube. It's made up of squares, right? Correct? Correct? What is this? Anybody recognize this? Especially, it's actually quite popular in chemistry. So
Double. It's a tetrahedron, but it's
it's
two
not a
sides.
it's not a tetrahedron, sir. It's a square pyramid. 2 square pyramids joined with a square removed, right?
No, it's a polyhedron, right?
Yeah,
All
it's
that
a
you're saying.
Yeah, all I'm showing are polyhedra, but I'm asking what kind of polyhedra are they? So can you see a square pyramid on the top and a square pyramid on the bottom?
Okay, I don't know the name. No, it has a
Yeah,
name, and double something is there.
it's called an octahedron.
Octahedron, okay.
So if you see, it has 4 triangles up and 4 triangles down. So it has 4 triangles up and 4 triangles down. So it's an octahedron. So many molecules are octahedral in chemistry. You might have learned it in valence shell electron pair repulsion theory. So now the 2 shapes that I'm going to show you now are kind of exotic. It's kind of so I'm just showing you this now. So this shape is called as icosahedron. Okay. So what is happening here is there are 5 equilateral triangles on the top. So can you see what I'm showing? And then similarly 5 at the bottom. Okay. And then in the middle you have 10 equilateral triangles in the zigzag way, which are forming the. Can you see? So 5 equilateral triangles at the top.
So
5.
usually our satellites are in this shape only, right?
Yeah, I guess I have seen many. I've seen many things in this shape. So 5 at the top, 5 at the bottom, and 10 at the sides. So totally 20 equilateral triangles. That is why icosahedron. In Greek, icosa means 20. Okay. So this is another shape, and the final shape that I am going to show you is made up of regular pentagons. So see this. It's called. Let's count the number of faces first. So to start with the top 3 in red, okay, can you see the 3 red faces? They are at the top, and then 3 are at the bottom, so which are in blue. So the red and blue are at the bottom. Wait. Yeah, so the red and, sorry, not blue. Okay, this is top 3, bottom 3, and then side 6 pentagons, if you can see. So 3 plus 3 plus 6 is 12. So it's called a dodecahedron. Do means 2, deca means 10, dodeca is 12. So this is called a dodecahedron. So I have shown you 5 shapes now. 3 of them are already familiar to you. So cube, tetrahedron, and octahedron are familiar, and these 2 exotic beasts. So I just want you to tell me now, what are some nice properties shared by these 5 solids? What properties these polyhedra have in common?
What do you mean? They are
What
all
properties? They are all?
they can be written as ax less than or equal to b. That's all I
No,
can say.
no equations, only geometry. I mean, geometrically, what is very nice about these 5 solids? So what are they made up of? The faces. So the tetrahedron is made up of equilateral
Plane.
triangles. So the octahedron is also made up of equilateral triangles. The icosahedron is also made up of equilateral triangles. And cube is made up of square, and dodecahedron is made of cube. By the way, this is a dodecahedral version of Rubik's cube. So normal Rubik's cube has uh, 6 faces, right? So this is like a dodecahedral version. So you have 12 faces. You got aligned. So you can unscramble and scramble. So this is a dodecahedral cube. This is a novelty I ordered from Amazon. So there are many fancy stuff like dodecahedral calendars. Since it has 12 faces, you can print each month's calendar on the calendar. But then you can make a calendar display. There are lots of fancy stuff you can do with this. But geometrically, I just want you to take some time and tell me what is common in these 5 solids. So what is nice about these solids? Because the ancient Greeks are very, very obsessed with it, and they can't be obsessed with it without any reason, right?
Regular faces, right?
Yeah, yeah, regular faces. So all the faces are. I hear some noise. So all the. What is happening?
Somebody's mic is on. I
Yeah.
mean,
Akshit is in the lab, so for positive feedback is happening. So yeah, so all the faces are regular polygons, right? Equilateral triangle, square, regular pentagon, right? That
so
is one thing.
at each vertex, the sum of internal angles are 360 degrees.
No, 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 no. It's actually less than 360. We'll come back to that later. It's going miles and miles ahead. But there is something at each vertex that is very nice. If you look at this, each vertex looks the same. I mean, they are identical. For example, take the dodecahedron. So you see 3 pentagons meeting at a point, right, at each vertex. So if I flip this, it's still 3 pentagons meeting at a point in this vertex as well. So whatever vertex you go, the environment looks the same, right? Correct? There is some very nice symmetry about this polyhedra. Whatever vertex you go, the environment looks the same. If you take a tetrahedron, if you take the top vertex, it is 3 equilateral triangles meeting at a point. If you take some other vertex, it's the same 3 equilateral triangles meeting at a point. No matter whatever vertex you take, you see that the environment is same. You have the identical polygons meeting in an identical way at every vertex, right? Correct? Yes or no? Can you get it? Okay. So that is one thing. Another thing that is very important is these polyhedra are called convex polyhedra. So convexity is a very geometrical notion. What it basically means is this. In Greek, all polyhedra are convex by definition, because in Greek, hedra means seat. So seat, why seat is that, if you take any face, for example, I take this blue face, I can, support the polyhedron on this blue face such that the entire polyhedron lies on one side of the plane containing the blue face, correct? So mathematically, this blue face acts as a supporting hyperplane in convex analysis, if you have read. But physically what it means is that, each face can serve as the resting resting face for a polyhedron, it can be supported on each face. For example, if you take a non-convex polyhedra, you cannot support all faces. For example, if you take a Christmas star, if you take, you can't support it on any of the inner faces, right? So that is not a convex polyhedra. Whereas this, if you take, whatever face you take, you can support the polyhedra. You can place the polyhedra on a table such that that face is in contact with the plane that you are given, right? So that is what is convexity. So we see that these polyhedra are symmetric at each vertex. They are convex and they are made up of regular polygons. Correct? So do you get the three properties? They are identical at each vertex. They are convex and they are made up of identical regular polygons. So you have either only squares or only triangles, equilateral triangles, or only regular pentagons, or only squares, right? So these are the four special properties. You have one set of polygons that is making up the entire polyhedra, and that one polygon is regular. It's a copy of a regular polygon used for each face. And then you have each vertex is symmetric, it's the same environment around each vertex, you can't distinguish between one vertex and the other vertex, the environment is the same. So these five solids have those properties, and the very beautiful thing about what the Greeks showed is that these five solids are the only polyhedra having the properties, these four properties that I mentioned. These five are the only polyhedra possible that are convex, symmetric, and made up of one regular polygon with that one regular polygon copies of that making a beach face. So these five solids are called Platonic solids. So named after Plato, a Greek philosopher and mathematician. So we are going to use these five solids to teach some really cool stuff. Okay, so I presume you all are familiar with high school geometry, geometry of the plane, properties of triangles, squares, circles, and so on. So can you recall some theorems from high school geometry? High school geometry of the plane.
Sum of the internal angles of a triangle is 180.
Yeah, that is one nice theorem. Another theorem. What?
You have axioms and postulates building up to higher, more complex things, right?
Yeah,
That's the
yeah. That's okay. I have some theorems that you proved using those axioms and postulates. Some results. So one
Sum
result
of
is sum of,
exterior angle in polygon is 360 degree.
yeah. In fact, that is a generalization of the interior angle theorem of triangle. Yeah, that is very one important result. Sum of exterior angle of a polygon is 360. It's very, very important. We will come back to it later. Anything else? So come on, there are so many theorems that haunted you in high school, right? I don't know. At least I was scared of triangles in high school. Okay, what about Pythagoras theorem? It's a nightmare, right? I mean, the statement is simple, but it isn't very obvious at all, right? Anybody still remember the proof of the Pythagoras theorem? Geometric proof, not, I guess not. Okay, so what's the area of a circle? Area of a circle? Yeah, pi r square. So, okay. So these are some of the results that you did in high school geometry. So now what we will do is I want to introduce you to something called as intrinsic geometry. That is very, very important. So for this, what I want you to imagine is, let's say you are an ant. Okay, you are an ant living in the surface of one of these polyhedra. Okay, let's say you are an ant living on the free to move about in the surface of the polyhedra, but you don't know of the world outside this polyhedra. All you can do is you can see whatever is in this polyhedra. So you can visit all the points in the polyhedra, you can see all of them. So, but you can't, you don't know of the world outside this polyhedra. For example, you don't know about my hand, or you don't know about me, or just your world is just a polyhedra. In fact, that is how people were before the invention of technologies. We are also like ants on the Earth's surface, right? We know only about the Earth. In fact, we know about the sky because we have the capacity to look up. But imagine that you are a pig or something where you can't look up the sky. You can look only some local neighborhood of the Earth's surface at an instant. So like a pig on the surface of the Earth, imagine that there is an ant in the surface of a polyhedra. So now what I want to show is that how an ant will feel about the geometry of this polyhedron's surface. So that's what I'll be going to illustrate now. For this, what I'm going to do is I'm going to just take away one of the pieces of the polyhedra. Okay. So let's take this face now. So imagine now that the ant is confined to this face. It can't move out of this face. Okay. It is, it's a very small ant, let's say it's in the center of this face, and it can't move about much, okay, and it can't see much. I will just mark this. Can you see the black dot? Can you see the black dot? Okay. So now, the thing is that for this ant that is confined to the surface of this face alone, the entire, this looks flat, right? It looks like a part of a Euclidean plane, right? This face, correct? So the ant can fantasize a plane that extends this pentagonal face, and imagine this, yellow thing as a part of an infinite plane, correct? Am I right? Correct?
Yes.
So let's call that, let's say, a fantasy plane. People, differential geometry people call it tangent plane or something. Let's call it, let's say the fantasized infinite plane that extends this face. Okay. Now, this ant can imagine this pentagonal face as a part of this, as a part of that fantasized infinite plane, right? Now, in this infinite plane that the ant imagines, of which this yellow face is a part of, all of Euclid's geometry will hold good, right? Whatever high school geometry you studied in the plane will hold true, right? In this, am I right? If you draw a triangle, let's say like this, the angles will add up to 180, right? If I draw any polygon, the exterior angles will add to 360 within this neighborhood. And if I draw a right angle triangle, Pythagoras theorem holds. All this is true, right? And if I draw a circle, the value of pi is 3.1416 or whatever, right? Correct? This is simple to visualize, right? Correct? Correct?
Yes.
Okay. So now what I'm going to do is I'm going to increase the accessible region of this ant, instead of seeing just this one face. So earlier the ant could see only this one face, okay? Earlier the ant could see only this yellow. But now imagine that the ant can see the other red face that is above this. So can you see the red face above this, whatever hole is? This hole is the yellow face. So imagine the ant can see the yellow and the red. Okay, I'll just take away the red face. So imagine how the yellow and the red looks together. Okay, the yellow is at some angle and then the red is bent, right? The red looks bent to you, right? The yellow and the red looks bent relative to each other, right? Am I right? The yellow and the red look bent with respect to each other, right? Correct?
Yes.
So now I'll take the red face now. So imagine now the ant can see the yellow and the red face now. So both, it can see both. Okay, they are bent, correct? It was bent. I forgot the exact angle, but they were bent like this. Can you see the bend? It was bent. It was not like this. It's like this, right? Something like this or like this, right? Correct? Correct? Correct?
Yeah.
Now, let's imagine the ant can now access both this yellow and the red plane, okay? It can travel freely in both yellow and the red plane, but at the boundary, imagine there are some people who are restricting access to what is beyond, okay? But it can freely tour the yellow and the red plane. For you, a three-dimensional beast like you, the yellow and the red plane look bent relative to each other. So in some sense, the yellow-red region is not flat in a three-dimensional sense, right? Correct? The yellow-red region together, it looks bent to you, and it's not flat as a three-dimensional observer, right? But how will an
Yes.
ant feel? How will an ant feel if it able to see the yellow and the red together? Can the ant imagine the yellow and the red faces together as a part of an infinite Euclidean plane and do all the Euclidean geometry stuff on that? What do you think?
No.
Why?
Well, it can feel the change, right?
No,
It can
an
feel.
ant, see, we can see the bend. Can the ant feel the bend intrinsically? For example, for an ant, when it goes from the yellow to the red face, will it suddenly feel that, sum of angles of triangles is not 180 or whatever?
In that sense, no.
So let's say that I undo the bend now, it's totally flat, correct? Can you see the flat thing now? The yellow and the red are now totally not bent relative to my eyes, correct? Now I draw a triangle like this. Can you see the triangle that straddles both the yellow and the red face? Okay.
Yes.
Now let's say that this is the plane that the ant is imagining. This yellow and the red to be a part of. This is flat to us also, right? This looks flat to us also, right? Correct? Now let's say this yellow-red flat plane, which are not bent related to each other, is the fantasized plane that the ant imagines. And now I create a bend. Now, doing this bend, will it change any intrinsic property of the triangle? Suddenly will the angles, change, or will the side lengths change or whatever? Will it happen? Will they happen?
No.
Let's say, no, right? The ant won't feel anything, right? It won't see any, the geometry of the triangle won't be altered, right? If I do this bend. Correct? Correct. So, what I want to say is that the geometry that is intrinsic to the ant is unchanged when you bend. So, always the ant can imagine the unbent plane and do all the geometry on it. You, being an external observer, bending these two faces will not affect the intrinsic geometry of the surface, correct? It can still imagine this unbent plane and then imagine this yellow-red unbent configuration as where this can be the fantasy that the ant imagines that it is on, even though the reality is this, because this is no different from this for the ant, because nothing geometrically changes in the surface. Only to you in the three-dimensional ambient space, it is bent, right? Correct?
Can you repeat? I just got a phone call. So just a few. I don't know
What
what you were saying.
so now the yellow and the red faces are not bent, right? They are not bent, right? It's flat. Both of them are flat and lying in the same plane, right? The yellow and the red. Correct? The yellow and the red are now in the same plane, right? They are not bent, right?
Yeah.
But in the original polyhedra, they were bent, right? Because all the faces are bent. In the original polyhedra, which is this, all the faces are bent, right? Blue
Yeah.
is bent relative to pink.
Yeah.
What I'm claiming is that this bending does not change anything intrinsic in the surface. If I draw a triangle that straddles both the yellow and the red face, nothing about it changes when I do this bend, if you see.
Yeah.
Nothing about it changes geometrically inside the surface, in the
Yes.
surface. So what I'm saying is that the intrinsic geometry of the surface doesn't change when it is bent, when these bends happen.
Hmm.
Correct? That's my claim.
Okay.
Now, so earlier these two were the faces, right? So this yellow and red, right? This yellow and the red, the holes that are there. Now what I do is, I take up another face that comes from this vertex. So I'll take another red that is joined here. So I took away the yellow and the red here, right? I will take, let's say, this yellow also I will take, okay? I will take away this yellow also, so if I take away this, now what I will get is, I'll just build it and get back. Yeah, this is this. Now I take away. I take this. I'll just rub it. Correct. I take away three faces now, which meet at a vertex. Can you see this? This vertex should have been sitting as a part of the polyhedron, but I have forcibly taken it. I have forcibly taken it. Can you see this vertex? Correct. Can you see this vertex?
Yes.
I will use another color to distinguish. So because it will be very convenient, I will use a green rather than another yellow. So you see this yellow, red, and green. This is the vertex that I have stripped out from the polyhedron. Can you see this? Okay. Now imagine the ant can have access to yellow, red, and green, both all the three faces. Correct. It can straddle the regions of all the three faces. Now, do you think will an ant feel wrong? Something wrong with the surface, Can the ant fantasize the yellow, red, green together as a part of an infinite Euclidean plane where sum of angles of a triangle is 180, where area of a circle is pi r square and all those usual stuff like that? Can the ant imagine these three together as a part of a larger infinite plane intrinsically, even though extrinsically it's not a part of a plane, we know they are bent. But intrinsically, can the ant feel that this three things together is a part of a single infinite plane?
Yes.
What do you think?
Yes.
Okay, let's check the claim. I will draw a circle with the vertex at the center, okay? So, take the vertex as the center, I am going to draw a circle, okay? Can you see the vertex? So, I will draw a circle, let's say, I will draw a circle and get back to you. Let's say of some length, which I don't care, honestly. Correct, can you see a circle? Correct, can you see the circle with a vertex at the center? It may not look exactly like a circle, but imagine it's a circle. It is a circle in each plane. In the yellow plane alone, that is an arc of a circle. In the red plane alone, I am drawing an arc of a circle. And the green plane alone, I am drawing an arc of a circle of the same radius. That will be the vertex, circle in this vertex, right? With the vertex at the center. Correct? Can you see it? Okay. Now, what is the circumference by diameter of this circle? What do you think it is? If it were an Euclidean plane, what should be the circumference by diameter ratio? If it is an Euclidean plane? If it were an Euclidean plane, if it were a circle in the Euclidean space, what should be the ratio of circumference by diameter?
Pi.
Pi, right? But is it actually pi here?
No,
Yeah, why?
because the different arcs in the different three planes, they do not cover a 360-degree. They are like,
Exactly. The magic happens when I unwrap this. So I unwrap this. See? Can you see some gap when I unwrap this? So the sum of the arcs do not add up to 2 pi, right? 2 pi r, right? Correct? Correct. There is an angle defect. It's not a 360.
Yes.
You can see. Correct. So there is an angle defect. This is not a 360. Very, very amazing result this is. Now the thing is, this is not a circle. In this, this is not a circle here, right? When I show this and when I unwrap when I detach the yellow and the red and separate them, and when I treat the yellow, green, and the red as an unbent plane, it's not a circle here, right? It's just an arc of a circle. Correct. But when I make the polyhedron by pasting this yellow and the red, by creating the bend which creates the vertex, suddenly this becomes a circle in the surface, right? Correct. This is a circle in the surface, but it is not. But the arc length is not 2 pi r. The circumference is not 2 pi r. It is less than 2 pi r. Correct. Or imagine this as a unit length. The circumference is not 2 pi here. Because unwrap this, This not an this is the total arc length of circle is not 2 pi. It's less than 2 pi because there's an angle defect. The sum of angles of a pentagon, 3 of them, each angle is 108, right? 108 into 3 is not 360, it is something less than 360. The magic happens when you know, glue this yellow on the green or whatever. Correct? So this is not a Euclidean space. The thing is that if you take two faces separately, the ant can imagine these two faces as a part of a fantasized Euclidean plane. And if you take the red and the green separately, then also the ant can imagine the red and the green alone as a part of an infinite Euclidean plane. But the funny thing is, the plane that works for the red-green pair, it cannot work for the red-yellow pair as well. There is no single common fantasized plane that works, that the ant can imagine all the three faces as a part of. Because if it were imagines, you know, it is not Euclidean. You know, circumference of circle is not 2 pi. Unit circle is not 2 pi circumference, correct? Correct? So the creation of this vertex kind of is very important. It distorts the geometry around the around its neighborhood. It's not a Euclidean geometry around the neighborhood of a vertex. Something fancy is happening. Correct? Now let's look at other dear properties that you proved in high school. So what are the properties? Sum of angles of a triangle is 180, right? So again, let me draw a triangle. Let's see if the angles add up to 180. So I draw a triangle. Can you see? Correct? Can you see the triangle? Wait, let me draw darker. Correct? Can you see the triangle? So it's the sum of the angles of a triangle 180. This triangle, this black triangle I have drawn around this vertex. It's the sum of angles of a triangle. Is it 180 degree? I'm asking you. Definitely not. I unwrap this. What is this? This is not even a triangle, right? In the plane. This is something nonsensical. So the sum of angles of this beast is not 180 because it's not even a triangle when I unwrap it, right? You can see, you know, these two angles, if they are theta 1 and theta 2, that theta 3 is not the angle between these two straight lines in the yellow and the red plane. The yellow and the red line, they meet only when I make the vertex, only when I glue them. When I unwrap them and see the plane, it's not a triangle. So you cannot expect the angles of something that is not even a polygon to add up to 180. In fact, if you take physically a protractor and measure the angles of a triangle, it won't be 180 degree. You know, I leave it to you. If you come to the lab anytime, you can play with this and check for yourself. So if you take a protractor and measure the angle between, you know, first you unwrap the, first you take away the yellow and you take away the green. And first you look at the red yellow alone, okay, and then you measure the angle, and then you measure the angle in this face. Maybe I'll draw this triangle again. Erased, I guess. Some funny thing is happening here now because of this vertex. And this is what differential geometry is all about. I'll draw it again. Draw it again. Yeah, I hope it's visible. So if you take the yellow, red and green alone, you can unbend it and imagine this to be a plane, right? If I take away the yellow, then I'll have two sides of this triangle, right, in the red and green region, and you measure this angle. You measure this angle, this part of the angle. You measure this angle by, you know, taking away the faces and unbending it. And then you measure the angle in the red-yellow region by measuring this. And then you measure the angle in the yellow-green part by, you know, joining the yellow and the green and taking off the red. So I create the vertex again. I take back the red now instead of and then I unbend this, and then I measure the angle between these two lines. Okay, for each angle, take away the face containing the side that is not in the angle, and then you measure the angle by unbending it and then seeing the plane, and these three won't add up to 180. That is for sure. Okay, so you see something fun happening here. So triangles are not adding up to 180 degree, and I will show you something else funny that is happening now. Very, very important, and this is what led Einstein to, think
So I have a
about
question.
gravity. Yeah,
So since this is a regular polyhedron,
yeah,
everything, all the angles, everything is known,
yeah,
right? So for a given triangle of some length,
yeah.
can we calculate explicitly the deficit in the angle?
Exactly. That deficit we can calculate, and that is what characterizes the non-Euclideanness of the triangle or whatever of the vertex. That is called as curvature. I will get into that.
So in the limiting case, you get the plane. I mean, when the deficit becomes zero.
Yeah, when the deficit is zero, then it's intrinsically flat
Hmm.
because it's Euclidean. Everything, because if angles
And
add up to pi, then it is Euclidean, right?
so which polyhedron will have a maximum deficit for a given size of the triangle?
For a given,
For a given length of the triangle. So length
for
is fixed.
sir, the angle deficit can take any. I can always create a polyhedron with any angle deficit I want.
No, but for this platonic polyhedron, which one has the
Oh,
maximum
okay,
deficit?
yeah. For the platonic polyhedra, so this is the angle deficit, right? The gap between the red and the green, that is the angle deficit, right? Correct? The gap between the red and the green, this is the angle deficit, right? It should add to 360, but it is not. So this gap is the angle deficit from 360, right? Now, the thing is that lesser this gap is, less bent the vertex will look, or less sharper the vertex is. But a more sharper vertex, for example, if I take a tetrahedron, the vertex looks very sharp, right? So I expect it to have a much larger angle deficit, and it does have. I remove the bottom face and I take only the three faces meeting down. Okay, I remove the top face, and then I remove. So this is the tetrahedron with three top faces meeting in a vertex, and then I remove one of them. So you see, this has a much greater angle deficit. The angle should add up to 360 if it were Euclidean, but it's adding up to only 180, right? So because then this extra 180 degree is going to create the vertex here. So more sharper the edge, more deficit the angle. So your question
So are these angles some nice integer values, or and is there a relation between all the angles for the five
yeah,
platonic?
there is a relation, sir. The most sharpest of the polyhedron will be the biggest deficit, because we see the more the deficit, the more sharp the vertex is.
Yeah,
Right?
that is okay. But are there some kind of nice integer values, or like here you showed
Here it is 180. Here it is 180.
Yeah. So are there
And
some kind of
yeah, it is 360 degree minus the number of faces into the interior angle of each polygon in the face. It is 360 degree minus the number of, for example, if this is a pentagon, right? So it is 360 minus 3 pentagons, 3 into 108 degree, which is the angle of the pentagon. So 360 minus of 3 into 108, that is the angle deficit of a circle in the Euclidean, in the vertex. Correct?
okay? Yeah, got it.
So,
like this,
Ram Session, I have
Yes.
a non-mathematical question.
yeah,
Say you take a football.
yeah,
Football is a polyhedron,
yeah.
stitched like a polyhedron. I
Yeah,
think it's pentagon or hexagon, I don't know.
It is both. It has both. The black colors are pentagons. The white colors are hexagons. There are two colors.
Oh, okay.
Correct.
So both pentagons and hexagons. It's very smooth.
Yeah. Yes, sir.
Almost a sphere.
Yeah, because the number of vertices are very large, right? And
That is correct.
So yeah.
So if you draw a triangle or some or a circle,
yeah,
the deficit, will it appear very large?
the deficit what? The angle will
If you
appear
draw a
large.
triangle the deficit for the triangle.
It depends on the how many vertices the triangle encloses. This is for a triangle that encloses only one vertex, what I said now.
No, it's not very sharp, no, as you're pointing out.
Yeah, it is not very sharp, but if the triangle encloses more vertices, the deficits can add up, right?
No, three vertices only.
Football has only 3 vertices, sir.
No,
I
no,
don't
you
get
can't
you.
have, right? 3 or you have 4.
So football
So
has many
if I draw a
vertices, right?
triangle, if I
Yeah.
draw a triangle, I can't draw it in 3
No,
vertices,
no.
or
He
can
means
I?
to say at each vertex there will be either a 3 or 4 pentagons or hexagons. That is what he is saying.
Yeah, it is 360 degree minus the sum of the angles of a polygons meeting. That is the
Pentagon or
angle
hexagon,
deficit.
but it's not very sharp.
Yeah, it's not very sharp, sir, at each vertex because because that you need the football to be not very sharp, right? That's
Okay,
how you
so
want
each
to.
vertex is four patches.
Yeah. Four polygons meeting. I think 1 pentagon and 3 hexagons, I guess, in a football
Yeah.
at every
So if you
vertex.
draw a triangle,
Yeah.
uh,
Triangle enclosing how many vertices? Here the triangle enclosed only one vertex, right?
it's a only one vertex.
Then the
Football.
angle deficit will be 360 minus the number of the sum of the interior angles at the vertex. That will be the angle deficit. Whatever. Like for example, I can have a. For example, I built something where it is.
No, it's not as sharp as it looks, right?
Yes, sir. It's not as sharp
So
because
the
the number
deficit
of
must be small. Is that your claim?
the deficit at each vertex is small. Yeah.
It must be small.
Yeah. If it is not sharp that much, the deficit is small.
But it's not Euclid, right? It's
Yeah,
a
it's
sphere.
not Euclidean. Sphere is not Euclidean. If a spherical triangle doesn't have 180 degree sum of angle of triangles.
I understand that.
Yeah.
No, if the sharpness is not there, but it is quite far away from Platon, Euclid.
It is quite. Yes, sir, because at each vertex there is not much sharpness, right? But there are many vertices compared to, let's say, this dodecahedron, right? So the angle deficit is that I'm saying is only for a triangle that encloses only one vertex. If the triangle has a reasonably sized triangle in a football will have more and more vertices that are inside the triangle, right? Then the angle vertices of that will add up.
Okay, carry on.
So I guess you got a flavor of this angle deficit leading to strange properties, non-Euclideanness around this. Okay, the thing is that if you take the yellow green alone, I can imagine this as a Euclidean. If I take the red and green alone, I can imagine this as Euclidean. Red and yellow, Euclidean. But if I take the 3 together, I can't imagine a common fantasized plane that kind of, that I can imagine this vertex environment to be a part of. Because if I imagine, I find that circles don't have 2 pi circumference, unit circles don't have 2 pi circumference, all those fancy stuff happening. Now another very important thing that's happening is what is called as parallel transport. That is very, very important in differential geometry. So I will illustrate that now. So let's take a cube for instance this time. So in a cube, 3 squares meet at a point, right? So these are 3 squares, they add up to 270. So the angle defect is 90 degree. So I join like this to create a cube, right? This is 3 vertices of a cube, right? Correct? Correct? So
Yes.
what I will do now is I will take a line. I think I need another marker. One second.
Unmute yourself. Ramshishan, unmute.
Now okay. So I take a straight line into it is straight because if I unbend it, it will look straight. So I take a straight line. Can you see the straight line? I'll just straighten it. Can you see the straight line? Okay.
Yes.
So now what I will do is, let us say there are two ants that are starting parallel on this straight line. Okay. So let's say there is ant 1 that is moving 90 degrees perpendicular from this line, and then there is an ant 2 that is moving perpendicular from this line. Okay. So the ants are taking a walk. Can you see the direction of their movements? Correct. So they all start parallelly, right? They are parallel initially. Correct. Because both of them are 90 degrees. I hope you can see the perpendicularness. Correct. Each ant makes an angle of 90 degree with the line. Correct. Now what I do is, let's say the ants continue. Let's say the ants move at equal speed in the same direction. They continue moving straight in the same direction they started. They move for some length, some common length. So the ant moves like this, and then it will enter the boundary between this boundary, and then this ant will move like this. It will encounter this boundary, and so if I join the face this again and make a cube. So I hope you can see this now. So this is the ants, two ants. So this is ant 1 and this is ant 2. Can you see? 1 and 2, correct? So they are starting like this. And then they are continuing straight. So what this ant 1 is doing is, if it encounters a boundary that takes it to some other plane, it will unbend the pair. It will unbend the pair of faces that it is, which share that edge. It will unbend and continue moving straight in that direction. It will continue moving straight. So this ant, I will show the trajectory of this. It starts from here, goes like this, and then keeps going straight. And then this ant also same thing. It starts from here, moves like this, and then keeps going straight. Correct? Can you see it? Can you see it? Now let's say what we expect when this happens in the Euclidean space. So I will use the board now. Can you hear me now clearly?
Yeah.
So I will draw. So this is ant 1 and this is ant 1, this is ant 2, okay? And can you see what I am drawing?
Yeah.
I think I'll draw it. It is visible. So they are starting perpendicular. So this is what this ant is starting. And this ant is starting again perpendicular. They both travel the same length. Can you see what is happening? The first ant travels for some, let's say 1 meters. And this ant also travels for 1 meters, correct? Both of them are traveling the equal distance in the same direction, correct? So initially they were at AB, now they are at A dash, B dash. Can you see AB to A dash, B dash?
Yes.
So initially let's say they are separated by some distance x. Let's say this is x. What will be the separation after they move?
X.
X, right?
60.
Very obvious, because this separation also will be x, right? And they will still be 90, right? Correct? Correct?
Yes.
So then they complete a rectangle. These ants complete a rectangle. You can see A dash, B dash. It's a rectangle, right? Correct?
Yes.
So parallel lines remain equidistant in the Euclidean space. Can you get it? Parallel lines remain equidistant in in the Euclidean space. They are not attractive, they are not repelled, they remain equidistant. So if you take a walk with your friend in space, and if you start off in the same direction, after a while you will still be separated by the same amount if you are separated by x. So in other words, you say I am standing here, I am holding hands with some other person. Okay, so let's say Akshit is, I'm holding hands with Akshit, and if we walk, both of us walk x meters. Akshit also walks x meters. Imagine Akshit is at the other side. Then after a while, this hand will not be stretched or compressed because separation is the same. Can you feel it? Because this is a rectangle, right? Correct. Now let's see what happens in the cube when the same thing happens in the cube. So can you hear me now? So parallel lines remain equidistant in Euclidean space, and that's how you get rectangles. So the existence of rectangles in the Euclidean plane is a testimony to the fact that parallel lines remain equidistant. Is it okay? If parallel lines never remain equidistant, then you can't get a rectangle. This A dash, B dash won't be a rectangle. Correct? Yeah, right? So now I repeat this exercise. Just a minute. I'll get a marker of another color. So let's take the good old friend or ant, this time in the curved space like cube. Some funny things will happen which you never expected. So I'll draw the straight line again. So the black line is the vertical line. So yeah, I unbend this. So this is the vertical black line. The ants. So initially the ant is at one ant is at A. The other ant is at B. Fine. Correct. Now they as usual hold hands like couples and then they walk. I think I'll use a violet, or I hope I use a green. Which is better, violet or a green? I think green. So let's say this these two ants, they walk holding hands parallelly. Okay, so they walk for a while, and after that, so this is green. So the green, and then the other ant, I will color it using orange. Can you see the green and orange? Can you distinguish that the upper thing is green and the below thing is orange? I hope so. Correct? Correct? Can you say something? So what this ant B, bottom ant, does is it keeps going along for some length in this interface. Correct? So the ant B, it was here and then now it is here. So it unbends this interface and then keeps going straight for some length. Can you see this? The continuation of the orange trajectory. Can you see this?
Yes.
Now what I do is I will do what ant A does. So what ant A does is it encounters another interface like this. It encounters the other interface. So now it will, I'll unwrap like this. And now the ant A keeps going straight now in this, according to this interface, because all the ant bothers is it has to keep moving straight. And then it moves for the same length. Correct? So the ant moves for some length from A to A dash. Correct? Can you see A dash? Can you see A dash?
Yes.
Yes.
And ant B ant B now moves from B to B dash. Wait, just a minute. One second. Oh. So A to A dash. But if you look at ant B, this is B, right? This is B, right? Remember? Can you remember B? What I find here is the ant B, it moves in the orange line, right? From B to B dash. But what it sees is that B dash is same as A dash. That's what it sees because this is A dash, remember. Correct? I hope you can see this. Now
Yes.
I will make the cube like this. So initially they started like this. So parallel lines are meeting. Very, very funny thing. So correct, this was the initial separation, right? Now this ant, it started like this and then it kept moving straight for some distance. Now the other ant, what it does is it started like this and then it keeps moving for straight. But what we saw, it started like this and then it keeps moving straight. But what we find is this green and this orange, they actually meet. So in this space, what is happening here is funny thing. I'll just remove my. Can you see this? This is what is happening. You know, they start off parallel. Can you see what I have written? Can you see? Hello? So what I have written?
Yeah.
So the turning point is nothing intrinsically funny because we saw that an edge can be straightened, an edge can be unbent and straightened, and each ant is keeping on moving straight only. But what is happening here is that an ant at the top, it goes straight relative to the interface it encounters. The bottom ant moves straight relative to the interface, some other interface that it encounters. So we see that there are three phases. So the pair of interface that the ant 1 encounters is different from the pair of interface that the ant 2 encounters. Even though each are going straight, along their own ways, but they meet even though they started parallel. Can you see the fun happening? So there's something really wrong. Correct? Can you see what is happening now? So parallel, see, even though they are moving straight and they started off parallel, it looks as though they are attracted to each other. So if I hold hands with someone and then we walk in the same direction together in a non-Euclidean space, we both walk straight together, start off parallelly, we walk with the same speed. In a non-Euclidean space, what will happen is the length of my hands, our hands will get compressed or stretched. Here it is compressed because it's attracted, coming together. Can you see it? The most important thing, the reason why this happens is because of this vertex. This vertex is what is creating the non-Euclideanness. It's making the geometry really, really funny. I hope you can.
So I have a question. So if the ants move in opposite direction, they will diverge? But
they will still meet at some other. They will meet. They will still meet.
Some
only.
other phase they will meet.
Yeah. At some other point they will meet.
So they will eventually meet.
Yeah, they will eventually meet and then they will again diverge. They will meet again. You can sketch the full trajectory if you come to the lab, and then you can keep on sketching the keep on continuing the trajectory, keep on moving straight. You can actually see a nice dance happening. They meet and then they diverge again, and then they meet. There will be an oscillation. So, for those who are familiar with spherical geometry, two geodesics on a sphere, if they start off parallel, they will meet and then they will diverge again. They will meet, so you get this nice thing. That's what will happen. But I hope you now understand that parallel lines are attracted in a non-Euclidean space. Is that clear at least? Correct. So now I will show you another example where parallel lines diverge. So for that, what we need to do is, instead of an angle deficit, we need an angle excess. So I take, what is the angle of each triangle? What is an angle of each equilateral triangle? 60, right? Correct? Correct? Hello? Yeah, so if I have 6 equilateral triangles, then there will be no angle deficit, right? If there are 6 equilateral triangles, there will be no angle deficit, right? You can see here. Correct? 6, 1 top 3, bottom 3. Now what if I have 7? Then I will have an angle excess. So if I have 7, I will have an angle excess, right? This 7, there is no space. Maybe I can draw, I'll show the 7th triangle in some other color so that, see, there is no space for this 7th guy. It's just, stuck, protruding. I hope you can see it. Correct? Correct?
Yes.
Now what I will do is, I will make this, I will glue this and make a vertex. That is something. Can you see it, what I am doing? A bit of crazy.
Yes.
So this now has an angle excess instead of an angle deficit. The circumference of a unit circle is not greater than 2 pi now. Now imagine a polyhedra with a bunch of vertices like this. And here what you can show that parallel lines will actually diverge. So again I take 2 ants. So this is a straight line. Okay. And then I have an ant here again and an ant B. So trust me that they are equal length. You can verify yourself and see. So they would have formed a rectangle if all were fine. So this is the trajectory of the green trajectory now. It is straight perpendicular to the black. And then I'll draw another orange trajectory like this. Of the same length. Of course, you have to trust me that it's of the same length. I'm just using my fingers to measure. So I complete the triangle like this. I complete this path. So all are straight in their own respective domains. So these are the trajectories. I'll just show you. These are the trajectories of that same ant. Can you see the black, green and the red? Can you see the black, green and the red approximately? So they all start off same, correct? They all start like this. Can you see? Flat, parallel to each other, correct? Now let's look at the distance now, final distance. So you see this is final distance is actually much bigger than this distance, correct? Let's just look at this. This initial black thing is actually much bigger than this thing, right? I'll draw the final distance by another black line so that you can see it. It's actually very obvious for me because I'm looking at it in live. This is before. So each of them travels straight, this ant keeps traveling straight like this, and this ant also keeps straight like this. But their final separation is, like this. This is much bigger than this, right? This and this, correct? Can you see?
Yes. Yes.
So you see they diverge here. So all the rectangles don't exist in such a non-Euclidean space. There are no rectangles. Circles don't have 2 pi circumference. Unit circles don't have 2 pi circumference. Parallel lines don't stay parallel. It's just bewildering. So approximately. So this is one thing. The thing is, locally, if an ant stays in just one phase or at max 2 phases, it can pretend that one phase or 2 phase is intrinsically a part of a bigger tangent plane or the fantasy Euclidean plane of which this is a part of. But it cannot have. But the thing is, in the neighborhood of a vertex. So let's say this is a vertex, and there is a neighborhood of a vertex. Then even though each pair of faces can be imagined as intrinsically Euclidean, there is no single plane that fits the descriptions of all the pairs together simultaneously. For these 2 pairs you may create a fantasy. For these 2 pairs you may create a fantasized plane by unbending this you may create one fantasy, and then by unbending this you can create another fantasy. But there is no single plane that kind of describes simultaneously the neighborhood of a vertex in full neighborhood, even though partly it's okay. Yes sir, you raised a hand.
Yeah, I have a question.
Yeah.
So you took you took the geometry and showed how things collapse there. Okay,
Yeah.
all the vertices and all.
Yeah.
So what other things are there? I mean, what other math objects are there which gets preserved, which are not destroyed at those vertices or as you go from one phase to another phase? So is there some nice study on that?
What other objects are preserved? Sir, geometrical objects that are confined to the single phase, that is preserved, at least in polyhedra.
No, that I understand. Okay, so you showed how so you had this object of which is a polyhedron, right? And you took up a geometry, right? And you showed how the geometry gets. I mean, it's nothing holds as it is in the Euclidean space. Right? So my question is, are there other mathematical things that get preserved?
Geometrically, there are no geometrical things that get preserved, but topological ideas get preserved.
For example, you showed the circle, right?
Yeah.
So the circle on the plane and the circle on the vertex, but topologically still equivalent, right?
Yeah, topological properties are preserved because topologically, I may not. If you look at this 3 pentagon pair, where is? Wait, I think okay, I'll just create another 3 pentagon pair. Just a minute. Yeah, this is. So there is no way I can collapse these 3 pentagon faces into the plane. If I try it, I will kind of end up destroying this beautiful kit that I purchased. There is no way I can, unless I smash it and distort it or, cut discontinuously, let's say like this, I can never flat this. To flat this, I have to make a cut. There is no way without a cut I can flat this entire neighborhood of the vertex. But pairwise, each pair I can flat it, by unbending each pair, I can, flatten each pair of faces. But all the three faces simultaneously, I cannot flatten it without kind of smashing it, without creating a discontinuity. Even though, topologically, I can convert this vertex into a plane, right? Just imagine, just a minute. Just imagine this pentagonal, three pentagon face. Just imagine them as elastic objects. Imagine them as, let's say smooth like, pizza dough. Then I can smash them into a plane, right? Correct? Imagine these as elastic pizza dough. Then I can obviously smash them into flatten it, right? So topologically, this is Euclidean, this environment. But geometrically, it is not Euclidean. That's all I wanted to say. Correct?
Okay.
Is it fine?
Yeah, fine, go ahead.
So you can also check, you can draw a right angle triangle and, Pythagoras theorem doesn't hold. There is no concept of sine theta, cos theta and all in this kind of spaces because, the trigonometric ratios are independent of the triangle. So if you take sine theta, which is opposite side by hypotenuse, right? But you know that in Euclidean space, that ratio is independent of the exact right angle triangle you choose. In Euclidean space, you trust that if you take any right angle triangle, the opposite by hypotenuse of an angle is depending only on the angle, not on the exact triangle that you take, right? Correct? That depends on the fact that, the trigonometric ratios are independent of the exact right angle triangle because any two right angle triangles in Euclidean space sharing a same angle theta will be similar to each other, right? So the ratios will, get cancelled. But there are no similar triangles in non-Euclidean space. So for example, let's say you're buying a shoe from Amazon. So what you are seeing on the screen is not the actual dimension of the shoe, right? Correct? Then how are you able to decide if the shoe fits you or not? Because you have an idea that, the shoe that Amazon promises to give me will be an enlarged one. It will be very similar to the one that is shown on the screen, except that, the lens are all equally amplified. The angles are the same, but the lens are equally amplified. That is how you trust, right? In fact, that's how you trust a map of, let's say, Chennai, let's say. Of course, it's a map of Chennai. It's not a faithful geometric representation of Chennai because if you let's say if you want to go from the institute to the main gate, it's let's say 1 kilometer. Then the map is not in the map, but it's not 1 kilometer, right? But why do you trust the map? Because it is it is geometrically the same as Chennai, except that all the lengths involved are equally compressed. That's what you trust, right? In Euclidean space, correct? But in a non-Euclidean space, it's not possible. There are no similar triangles. If you have, if you want to enlarge a triangle by enlarging all the sides by the equal amounts, then the angles also will change. You can't have two triangles that whose lengths are all equally amplified, corresponding lengths are equally amplified with angles remaining the same. You can't have it. So, for example, let's say I attempt to draw a triangle around this vertex. So I'll draw two triangles around this vertex. So this is a funny thing. You can't scale objects in a non-Euclidean space. And it's very, very important. So maybe when the Amazon shoes, arrive at, or they send you the wrong shoe, maybe you can imagine that we are living in a non-Euclidean space or something. Just a minute. Oh, this got loose.
Unmute.
I'm drawing a triangle. This violet is worse. So this is a triangle. Okay. Now let's say I want to construct a similar triangle. What should I do? I have to let's say double all the lengths. Some ratio I choose alpha, I enlarge all the lengths by alpha. So what I will do is, let's say I equally, in fact if you have an exact scale you can do it. But so both the triangles that I have drawn are actually, their lengths, corresponding lengths are all equally amplified. I hope you trust me on that. But what I claim is the angles are not the same, as in Euclidean space. The angles are not the same because if I unwrap this, can you see the top and the bottom angle are not the same? Can you see? Can you see? Even though the sides are corresponding, the angles are not actually the same. Can you see?
Yeah.
So see, there are no similar triangles in non-Euclidean space. So the existence of similar triangles is a consequence of Euclidean geometry. It's not a non-Euclidean space. You can't scale objects in a non-Euclidean space, and that is very, very important because the concept of a scale is very, very, very fundamental to our human experience, right? Because we always imagine, something, or many things will fail if this fails. For example, I can't trust my architect that the house will be looking like what he describes. Yeah.
So all of geometry fails, or are there some exceptions?
Yeah. The thing is, geometry in the sense of Euclid fails. The thing is, you have to let go of. If you think geometry is Euclidean geometry, then it fails.
Okay, fine.
If you expect all the triangles to add up to 180 degree, if you expect similar triangles to exist, if you expect circles to be, having circumference 2 pi unit circles, then in that sense it fails.
Can
Okay,
you show
good.
that similar triangles thing again? That angle.
Yeah, this two triangles, all their lengths are equally amplified. The bottom one, the top one, and the lengths are all equally amplified, sir. But the angles are not the same. If I unwrap it, the angles are not the same. I invent this. So the top and the bottom angles are not the same. So even though the sides are correspondingly stretched, I will draw it on the board maybe. Can you see my construction? The sides, the corresponding sides are all equally amplified by alpha from the bottom to top.
Yeah.
If the space were Euclidean, the corresponding angles also will be equal. Correct? 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 That's what a similar triangle means, right?
Yeah.
So, whereas in a non-Euclidean space, because of the crazy bendings, it's not. That's what I showed. There is no concept of scaling in a non-Euclidean space. So the thing is that again, three squares forming a vertex as in a cube. So for each pair of faces, there is a Euclidean geometry. But there is no Euclidean geometry for the three faces put together. There is no, so it's like, there is no one ring to rule them all like that. There are rings to rule each pair, but there is no one ring to rule them all of them together. So it's like, in logic, there is a difference between the quantifiers. For example, there exists a fantasy plane for every pair of faces, but for every pair of faces, there does not exist a single fantasy plane. For each pair has one, but there is no single guy that works out for all the pairs. Can you get it? So in other words, if I put now the importance of this is this. So Euclid, was living long ago, thousands of years ago. So he claimed that he could derive all of geometry of the plane from just 5 postulates. So we all know what those postulates are, and we might have forgotten it. But the first 4 postulates were all very obvious. So the first postulate said that given 2 points, there exists a unique straight line joining them. That's not surprising. The second postulate said that given a straight line, you can always extend it to create a bigger line. That is not surprising. The third postulate, it said that all right angles are congruent, which means you can always move from you can always move on right angle like this to another right angle, without distorting distance and angle. So that is also obvious. And then the fourth postulate also claimed that given a point as a center and given a number r, you can always draw a circle with that radius r. So that is also not surprising. But the fifth postulate that he gave was very, 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 kind of. I'll just write it on the board. It will be majestic. How. So can you see what I have written? So what Euclid says in fifth postulate is consider 2 lines L1 and L2 coming from A and B. Okay, and let them make angle alpha and beta with the line segment AB. So what Euclid claims in the fifth postulate is the sum of the angles alpha and beta add up to less than 180 degree. Then the lines will eventually meet when they are extended. That's what he's claiming. Can you see it? Can you see it?
Yes.
Now the most fun part, okay? Although Euclid claims he treated all his postulates as equal, but he didn't. The thing is, he never uses the fifth postulate for the first 21 theorems. He never uses it. He's, kind of avoiding it, using it until it is really required. And only in the 21st theorem he uses it when he has to use, when he has no other choice. And let's say that Euclid uses the fifth postulate in proving theorem 21. Then in theorem 25, if he needs to use it again, he is not calling it directly. What he does is he calls it the theorem 21 for 25. He calls the result that was used, that was proven already using the fifth postulate. He is calling that, he's not calling the fifth postulate directly. He calls the theorems that are already proven using the fifth postulate. Can you get what I'm saying? Can you get what I'm saying? So in some sense, he is kind of discriminating. He says that, he's not really using it. He uses it only indirectly and only when it is really, really required. Because this postulate doesn't look intuitive at all to any. And what people hoped, what Euclid himself hoped was somebody eventually will prove this fifth postulate in terms of the other four. So what Euclid hoped was, somebody will eventually prove that the fifth postulate is not actually a postulate. It can be proven from the other four postulates and I can remove it. That's what he hoped. And for 1,000 years, people were trying to actually prove this. And there were actually many people who claimed that they proved this fifth postulate. There are many such false attempts, you can read. And there were many people who claimed that they have proven it. But the thing is that in their proof, they would have used some other assumption which was, which was unproven. So, one guy proved the fifth postulate, assuming that parallel lines are equidistant, which we just saw now. So, assuming parallel lines are equidistant, some guy claimed that he proved the fifth, some Arab guy, he claimed that he proved the fifth postulate. So, laterly people realized that, hey, this guy is using the fact that parallel lines are equidistant. But where does that come from, It turns out that that is actually equivalent to the fifth postulate itself. Parallel lines remain equidistant is actually equivalent to this statement, whatever I wrote now. And some other guy, claimed that he proved the fifth postulate, but in his proof he would have used something else. Maybe he might have used the fact that, let's say, similar triangles exist. So what this very famous mathematician called Wallis, he proved that one can prove fifth postulate assuming that similar triangles exist. And what he ended up proving was the fifth postulate is true, is equivalent to the statement that similar triangles exist, which we just now saw. And you see that, some other guy proved that the fifth postulate is true, is equal to the statement that, sum of angles of a triangle is 180 degree. So that was another, that's called, I think Legendre first showed that, the fifth postulate is equivalent to the statement that sum of angles of a triangle add up to 180 degrees. And you can see many other things. And another guy, he proved that fifth postulate is equivalent to Pythagoras theorem. So Pythagoras theorem we know, right? C square is a square plus b square in right angle triangle. So actually that Pythagoras theorem is equivalent to fifth postulate, whatever I wrote here. And the Pythagoras theorem is what gives us the distance formula in the Cartesian coordinate system, right? For example, you look at
Just a minute.
So can you see this? I'll just stop in a few minutes. So can you see this? Because this is the distance formula, right? Can you see this? So this is what leads to linear algebra, right? Linear algebra is all about the higher dimensional version of this. This is the bread and butter of linear algebra, and this is a consequence of Pythagoras theorem. Pythagoras theorem is actually equivalent to fifth postulate. So entire linear algebra actually owes a lot to this fifth postulate. So you see that all are cherished notions, But the thing is that the fifth postulate is not sadly, can be proven from the remaining four. If that were the case, then you would not have any non-Euclidean geometries like this, right? Because there are non-Euclidean geometries like this, the fifth postulate cannot hold. And the thing is that we saw that what Einstein realized was that parallel lines, so if two particles are there, they start parallelly, they keep moving straight, parallelly. If the space is curved, they look like they are attracted, right? They look like they are attracted. Correct? But
Yes.
if they were flowing, let's say there was a planet nearby and there's a gravitational force, then also they will flow attracted, right? Correct? They will be attracted like this, right? So what Einstein's flash was that maybe gravity is not a force. maybe the particles are moving actually in straight lines only. There is no gravity at all. Just that, what we think of as gravity is actually curvature of space-time rather than space. That's the only modification. Maybe what we think of as gravity is space-time. Curvature, the non-Euclideanness of this that leads to an attractive phenomenon like gravitation. That is the Einstein's. That is what Einstein's insight was all about. So what he realized was that gravity. So locally, an ant, if it moves only in one phase locally, then everything appears flat, right? There's nothing curve or nothing fancy. Similarly, locally, if you see, let's say I'm in a gravitational field of this planet Earth. Then let's say I am in an elevator or a lift that is falling freely under gravity. Let's say this mobile phone is a lift. It is freely falling under gravity, and somebody is stuck inside the lift. So for them, how will the motion look like? In their frame of reference, what will the motion be like? High school physics. When you are falling in the lift, when you are in a lift that is falling, then what will happen? Gravity will vanish, right? Correct? Correct? That's called weightlessness, right? Somebody is in a satellite orbiting around the Earth. They are in the satellite. They won't feel, astronauts feel weightless. Why? Because they are in a satellite frame, and the gravity vanishes because they are in an accelerating frame of reference, right? The satellite and them are accelerating in the same way, so they don't feel any gravitation, right? So locally, gravitation can be made to vanish in a small enough region. Similarly, locally, curvature can be made to vanish in a small enough region. When you stick only to one face, curvature can be made to vanish. It's only when you kind of patching up all the things together, you end up seeing something as curvature. Until then, there is no such thing as curvature. Locally, all faces are flat. When you want to patch up everything together, around a vertex, that's when you see funny stuff like curvature. Similarly, locally, gravity can be made to vanish, by in an accelerating frame. Just that, the value of acceleration will differ at each point, So there is no single accelerating frame that makes gravity vanish everywhere. That's the only thing, because the frame that is required to vanish gravity at each place is different. So there is no single frame to, make gravity vanish for all observers at all places. So this is what is the main idea behind, gravitation. So the only manifestation, as we say, the only way gravity affects the dynamics is that, parallel lines attract. So, if the, two observers, if they are separated and they start off parallelly, they will eventually get attracted in a space with, angle deficit non-Euclideanness. So we know gravity is always attractive, right? So it must be that it should always be an angle deficit like curvature, because only angle deficit like curvature will lead to attractiveness. And angle excess curvature will lead to something like this, repulsiveness. Since gravity is always attractive, there must be an angle. So what Einstein said was matter curves space-time, and the objects are moving in this curved space-time in as straight manner as possible. It's only because of the curvature you get attraction, not because of any force. And unlike curvature, gravity can be made to vanish in a small enough region. It's only when you want to make it vanish everywhere by connecting all those things, you get a problem. Similarly, Einstein saw a parallel between geometry and gravitation in physics. And then he connected these two. So the only thing is that you have to take time also into account. That maybe we can see some other time. But I hope very clear, because in textbooks what they do is they make fancy symbols and for example this thing of unbending, this thing of unbending and continuing straight, it's called parallel transport. And this kind of angle deficitness that we saw, it's called Gaussian curvature if you want to look it up more. But for higher dimensional spaces, you have to consider each set of surfaces. There will be many surfaces like this, and then you have to consider the curvature of each surface spanned by each in each pair of directions. So in a higher dimensional space, I take any two directions like this, for example, and then see the surface that emanates from these two directions, and then I see the Gaussian curvature, and then I take these two surface, and then I take these two. So that is called the curvature tensor. So curvature tensor, what it does is it takes two directions, and then it measures the this angle deficitness at each at that direction. So maybe if you want to refer more, I can send you my notes on differential geometry. I can share it with you. So I guess we can wrap up. Any questions? Any questions?
Okay, thanks, Ramseshan. Are we continuing? Are you going to give one more talk?
I can if people want it.
Yeah, maybe that space-time thing you can.
Yeah, we can include time.
Sure. Okay. Thank you.
Yeah.
Thank you, Ramseshan.
Thank you.